Introduction. Hello everyone. I'm with the Federal Institute of Hydrology in Germany, and together with my colleagues I'm working at a project called Seamless Prediction, where we try to improve forecasts by assessing uncertainty, using certain methods of error correction or data assimilation. And today I want to talk about the benefits we could or could not gain while assimilating snow water equivalent and soil moisture into our operational HBV model. So there are several waterways in Germany and several institutions dealing with navigational forecasting of water levels in those waterways, and you can see the individual reaches of the hydrodynamic model depicted there. And the DFG is responsible for water level forecasting at the River Rhine, whose catchment you can see over here. It starts at the German-Netherlands border and has an area of approximately 160,000 square kilometers. So we use the conceptual rainfall runoff model HBV to provide boundary conditions for a hydrodynamic model inside the main river, and well, we set up some test catchments for data assimilation. Here one at the Main River head catchment, and the River Lahn, and also the River Nahe, which I will talk about in this presentation. And the HBV model runs on a 1-hour time steps and provides lateral inflow to the hydrodynamic model, the main river reach, which then is used to make water level forecasts at navigationally relevant gauges along the river. So this is our HBV model, which was developed by the Swedish Meteorological and Hydrological Institute. And it uses a storage analogy to transform rainfall into runoff in subcatchments. So it has a storage for snow, which consists of a solid snow fraction and a liquid water fraction it can hold. It has a storage for soil moisture, which holds back part of the precipitation and passes a potential runoff to the runoff storages located downside of it. There we have the so-called upper zone storage, which produces a fast runoff component by the model, and also the lower zone storage, which produces something like base flow, and water percolates from the upper zone to the lower zone storage. The outflow from these two storages is then routed through some transformation function, which redistributes, makes a weighted redistribution of the runoff over time, and this is to get a proper shape of the hydrograph, which also has some implications for data assimilation. The soil moisture storage has a special role in this concept because it, as you can see, it doesn't produce any runoff at all. It just holds back some precipitation, but also internally it controls how quick the upper zone storage is drained and how much water percolates from the upper zone to the lower zone. And this is depending on the actual soil moisture index inside this storage. So we built a data assimilation procedure based on this concept. And we use ensemble Kalman filter to, together with observed discharges, to update the runoff storages, upper zone and lower zone. And also we use snow water equivalent from the SNOW4 model of the German Weather Service to update the snow storage. And we used HEPEX H14 product to its root soil moisture index to update the soil moisture storage of the HBV model. Also, this concept could be expanded to incorporate the H13 product of H-SAF, which is snow water equivalent to update the snow storages, but we had some data availability issues with that one. So I cannot actually show results about this. So the data assimilation approach. Shortly, data assimilation is about finding model state or initial condition which leads to a model simulation at a given time step which is consistent with observations. At the example of the upper zone and lower zone storages, which we update with observed runoff, we could say that we use the difference between observed runoff and simulated runoff and multiply it with some gain added to the soil moisture and to the upper zone and lower zone storages to get an update of those storages. And then we use those updated storages to get simulation results, which is much closer to the observed discharge. And we do this, we do update the upper zone and lower zone storage to mitigate wrong meltwater generation by the model in winter or to account for input uncertainties at the start of forecasts. Also, as I told before, there is some transformation function active in the HBV model which redistributes an instantaneous runoff from these two storages over some time steps in the future. This means, in fact, that these redistributed runoff superimposes with redistributed runoffs from other time steps, so that in fact the simulated runoff at one time step is depending on a number of upper zone and lower zone storages at preceding time steps, with this number being the length of this transformation function, which ranges between 11 and 14 hours in our test catchments. So we deal with this by updating, basically by updating the the runoff storages at the beginning of this time window of this transformation function, and propagate this state in time until the observation time step, and then do the analysis or store the initial conditions at that time step. So the procedure for updating snow storages and soil moisture storages is the same in principle, while we do not have a direct influence of this transformation function on these states. We do simultaneous assimilation of discharge and snow water equivalent or soil moisture index. So we have to update those states at a number of time steps before the observation as well. Also, we have to map those observations of soil water index to the actual model states. So the snow water index, snow water equivalent would be a sum of the solid and the liquid fraction of the snow storage, and the soil moisture index would be the soil moisture storage of the model normalized by the field capacity, which is actually a model parameter for every individual basin. Now to the data we used. The snow water equivalent data comes from the SNOW4 model of the German Weather Service, as I said, and this model simulates the past snow cover evolution in a region over Germany on an hourly time step with a grid resolution of 1 square kilometer. And yeah, it assimilates satellite observations of the snow mask, as well as in situ snow observations, to nudge the model results towards the observations. The advantage of this data is, of course, its high temporal and spatial evolution, but there's a downside to this, however, and this is the fact that this model overestimates snow accumulation in certain areas, and also this internal assimilation inside the model leads to jumps in the resulting time series of snow water equivalent, which looks something like this. Here you see the HBV snow water index equivalent in light blue, as well as the SNO4 snow water equivalent in dark blue. And the jumps you can see at these positions, which appear when a certain error threshold inside the model is met. And since the German Weather Service does not publish any information about the evolution of the model error, we cannot tell when those jumps occur. So somehow we have to deal with that. We could use H13 product of H-SAF, which is snow water equivalent on a 25-kilometer grid. And the benefit of this is that it is potentially consistent due to assimilating brightness temperature into regionalization of observed snow density, and also quality information for this data would be available. However, as Matthias Takala told, there have been some issues with the algorithm producing this data, so the data we have only covers this fraction of Germany, which in no way overlaps with our test catchments. Where here you can see this Main 1 head catchment and Lahn River and the Naur River I will talk about later. So and the third data we use is soil moisture index of the H14 product, which is a root zone soil moisture index up until 2.89 meters depth in 4 soil layers. And we use only the first 3 layers, which is about 1 meter, to assimilate. And one main advantage compared to other maybe soil moisture products of HEPEX is its continuous coverage, since it is also a model result which assimilates microwave observations of soil moisture into the model. The downside of this is that the relation of this soil moisture index to HBV soil moisture is not so clear, since it is not given that the HBV soil moisture is in fact some physically based value. So back again to the assimilation approach. We perform the data assimilation for the whole river catchment and sequentially for all sub-basins of this river, starting with the most upstream basin and then passing the results of this basin, updated results of this basin to the downstream basins and performing the updating there. And this is the Nahe river catchment consisting of 3 sub-basins. And I will mainly focus on this Nahe 2 sub-basin because the snow data evolution over there is most interesting from all 3 in the events I cover. Yeah, right. So what you can see here is the result of assimilating only this charge in winter 2010-2011 into the HBV model every 24 hours. And yeah, this figure is quite complicated, so bear with me. In the upper 2 panels, you can see the meteorological inputs with temperature here and precipitation there. Next panel is this snow water equivalent. Then comes the runoff storages, and finally the hydrographs from observations and simulation results. Also, these different line styles indicate with points the open loop simulation. Circles indicate observations of snow water equivalent and discharge. And those different colors of solid lines indicate with orange and purple this updating time step inside this transformation function. And this light blue and dark blue portions of the solid lines indicate the model propagation from the observation time step up until the next assimilation window. So as you can see here, only by updating the runoff storages in winter, we can have a big gain in simulation quality as compared to the open loop, which underestimates the peak of this melting event. But we have to keep in mind when we look at this portion of the figure that the snow storage of the model is not being touched by this assimilation approach. So we only update the upper zone and lower zone storages by observed discharge. So we add water to the upper zone to account for missing meltwater, or we subtract it when we have overestimation of observed discharge. So when we add, for example, water here to cope with the missing meltwater, we have to think that when we make forecasts from this time step on, at some point the snow melt will set in and we will have overestimation of observed discharges in the following time steps. So for this it would be beneficial to assimilate snow water equivalent into the model to limit the potential meltwater that can be generated by the model. You can see this here in this figure. So what we have done is, indicated by those orange and light blue lines, we have brought the modeled snow storage somehow in line with the observations, with some error included in it. And while the simulation results do not look that different from the previous ones, when we look at this melting event again, and especially look at this time step, we can see that this portion of the upper zone storage decreases after the observation time step, while when only assimilating discharges, it increases. In fact, in the same way as the open loop simulation at this point. So this is a sign that meltwater has been removed, potential meltwater has been removed from the system, and from this time step on, there's less water available to generate runoff. So we can await that forecast starting from this time step maybe would overestimate the observations in a much smaller way. So coming to forecasts now, I will show forecasts based on initial conditions from this time frame. The next slide, and while it is also crowded as the previous figures, I think we can figure this out. These are 5 forecasts, which are in fact perfect forecasts, which means they are driven by observed meteorological inputs, and they are spanning 14 days. And we are comparing observed runoff with open loop forecasts without any modification of the simulation results. Also, we take into account some corrected simulation results for which we used a simple autoregressive model to correct the model error which was observed in the past. And also this blue solid line indicates forecasts based on assimilated snow water equivalent and runoff, and the dashed light blue line indicates forecasts only based on assimilated runoff. So in the first forecast you can see that none of those forecasts hits the peak of the melt event at all. This is due to the fact that we don't have any information about this melting event at this point, which is the start of the forecast. However, you can see that the open loop simulation or forecast is well in line with the autoregressively corrected one, as well as with the forecast which is based on assimilated runoff. The forecast based on assimilated snowwater equivalent and runoff, however, fits the observed discharges in the decreasing portion of the wave quite nicely. And we can observe this through all the following forecasts. And the closer we come to the peak of the forecast, well, the better the assimilation takes into account that there's actually melting happened. And while at this point the assimilation added a lot of water, if we only assimilate observed discharges, the assimilation technique added a lot of water to the upper zone storage. So when the actual melt hits, there comes a lot of surplus water to this, and we get overestimation of observations. While when taking into account snowwater equivalent and assimilating it, we still have a very good fit to the observations. Yeah, and this spans all the portion of this decreasing wave. So now I want to show some results of assimilating soil moisture, or actually I'll start with just assimilating runoff in summer 2012. And what you can see here in this panel is the soil moisture index with dotted lines as the baseline HBV soil moisture index, and the circles is the H14 soil moisture index. And as you can see, it is twice as much as is simulated by HBV model. So, but we don't touch this here, we just assimilate discharge in this figure. So just by assimilating discharge, we can get a quite good fit in most of those small waves. However, in some cases, we cannot do anything about the increase and the overestimation, just because of the fact that the upper zone storage is quite empty at the beginning of those events. So we don't have any degrees of freedom to subtract water inside this transformation function window. And so the rainfall that comes inside this window just gives an overestimation that we cannot deal with. When we assimilate soil moisture index into the model, it degrades actually the model results in our case, because we double the soil moisture index of the model. And that's why the runoff generated by those small rainfall events becomes much more severe. And we cannot do anything about it, because at this point it appears that a direct assimilation of soil moisture index inside the model is not feasible. So again, some forecasts. And there are two things wrong in this figure. One thing is those two labels should be change their place. This one is without soil moisture index, this one is with soil moisture index. And the other thing is the scaling. So the only thing you can see in this figure is that the forecast based on assimilated soil moisture index overestimate the observations in all forecasts. While what you cannot see is just assimilating runoff gives us a good fit at those apparently small waves, which appear small because of the scaling. Sorry about that. Let's come to some more objective performance indicators, like the Nash-Sutcliffe efficiency as a lead time performance for these 14-day forecast. And in winter 2010, 11, and 12, we have a composite Nash-Sutcliffe efficiency of the forecasts when we assimilate snowwater equivalent and runoff that is higher than all, slightly higher over all 14 days of forecasting than the other three methods, only assimilating discharge, open loop, or autoregressive correction. In summer, however, when we do not assimilate soil moisture index, we see that the autoregressive correction drops below 0 even after 4 days. When we only assimilate runoff into the system, we get increase of lead time performance up to 7 days as compared to open loop. And if you wonder where the assimilated soil moisture index is, it is far below 0 with an extractive efficiency of up to -10. So a huge degradation in this case. To conclude, I want to say that updating HBV runoff storages with discharge gives optimal runoff at forecast start, and the persistence of this improvement is depending on the actual hydrological situation. If we update the snow water equivalent, we help to limit the available meltwater inside the system, which gives a slight improvement for greater lead times. And we could assume an equivalent improvement using the H13 product of H-SAF. And updating the soil moisture storage with soil moisture index degrades the simulation results, and we have yet to assess the possible benefit of rescaling those soil moisture index to HBV values. So that said, I thank you for your attention.
And for one question. I know that the soil moisture when you go to it's not very efficient, is it?
Yeah, that's
it's a fixed reservoir. It builds up. Means that when you have a completely saturated catchment, I mean there's not a lot of room for soil moisture, but it's still fixed in the HBV model. So, can you expect improvements when you update with the real data?
So the question was if we can expect improvements when updating soil moisture storage, which in fact is not physical at all. Well, and that's the question, if we get any benefit from it. It does control the runoff generation, as I said. So when the model simulates a wrong soil moisture storage, we could expect a wrong runoff simulation, which we could show in synthetic experiments, not shown here. So this is the question, if we could rescale the observations in some way that would be equivalent to the HBV soil moisture, this question is still open. And also the cost of this attempt maybe is too high to just use it. However, tomorrow you will maybe see results that are better than these, also using the HBV model of a different concept. Thank you.
Okay. Last presenter of the currently another job of the impact. The local industry in the region